How you doing, Abby? I just realized I forgot to change the due date on that worksheet and I switched it at 8 a.m. this morning. I hope I didn't like freak people out.
Oh, God.
The worksheet, it still said it was due this morning and I was like, oh crap. Yeah, it's due on Tuesday. Plus, to be honest with you, I think you'll get it done in class. Well, you'll get most of it done in class today. Fine, Dr. Nelson.
Wait, I'm gonna see the quantum mechanics math one.
Oh, did we already do that one? Oh, yeah, sorry. Oh, shoot, I changed the wrong. Ah! Shnikes. Jeez. Okay, I can't get anything right. Okay. Let's try to fix the damage I did. Okay, this was due.
I know it was a thing. I tried. I mean, I did it halfway.
Okay. Don't worry, that always happens. Oh, all right, now we got it in there. How you doing, Kaylee? Say good morning to Elise yet? Ask her, ask what she's gonna do this weekend.
Okay.
Good morning, Charlie. Good morning, Wyatt. All right, everybody, that's the bell. I can tell that by the energy in the room, it's Friday. So the plan is for today that we're going to kind of finish up everything we need on the math test. So we're going to cover de Broglie, Heisenberg. So there's like 2 pages of notes, and then I'll give you a half hour. So I do want to stop at, again, like 9:20, so that you guys can get a good half hour on your homework. Okay. Okay. So I'm gonna, before I get going here, guys, are there any questions that you Zoomies? Do you have any questions before we start taking notes for the day? And I'm muted. All right. That's good. We didn't get too far. All right, so we finished with Einstein. We did Einstein's equation, and so we've got basically two more equations to learn. So Planck said that light, which is a wave, can be a particle, and de Broglie is now just basically saying the opposite. Let's treat particles like waves. So treat a baseball like it's a sound wave. I know that sounds stupid, but that's exactly what we're going to do. All right, so we have two equations. We already have this equation, right? Hc over lambda equals energy. And we've got the Einstein equation, E equals mc squared. You see where I'm going with this, don't you, Isaac? I'm going to set these equal to each other. I'm going to bring lambda to the other side. Why? Because I want to. And then I'm going to divide both sides by mc squared. So that cancels, that cancels. One of my c's cancel. And so I'm left with h over mc is equal to lambda. So I'm going to make one little tweak to this. C stands for the speed of light, right? Well, I want this to be for any particle, not just light. I want this to work for baseballs, bowling balls, tables, pencils, anything made of mass. So the equation will then get altered to h over mv is equal to lambda. So v is your velocity, m is your mass. So there's your little proof on the de Broglie equation, how that came about. So what we're going to do now is we're going to calculate the wavelength of a person. Okay. And the guy in the video yesterday was Professor Dave, the science guy. He kind of alluded to this about, okay, what's the wavelength of a person? We're actually going to calculate it. Does anybody run track? Okay, so Hannah runs track. I'm going to guess that your best time is, let's see, 10 seconds. I bet you could run, 18 meters per second. So Hannah can run 18 meters per second. No, that's too fast.
Maybe like a 5-second. Well,
did the calculation wrong in my hand. Probably 18 miles per hour is a reasonable speed. So that would be 1.2 meters per second. There we go. There's your speed. 1.2 meters per second. Mass supposed to be in kilograms. Now we're going to calculate the wavelength. So remember, we have two values for Planck's constant. There's 3.99 times 10 to the negative 34th kilojoules per second per 1 mole. Or we've got 6.626 times 10 to the negative 34th joules times second per 1 particle. So are we dealing with a mole of Hannah's or just one Hannah? There's only one Hannah, right? So we use the 6.626. So we don't use that other Planck's constant. So if we're dealing with one electron, one neutron, one baseball, one whatever, all right, so now we just plug these numbers in. 6.626 times 10 to the negative 34th joules seconds per 1 Hana divided by 1.2 meters per second times 50 kilograms. Plug that in. So your wavelength is 1.1 times 10 to the negative 35th meters. Okay, and that's about the same for all of us. We all have about that wavelength because none of us can really move that fast. And even if you were to move super fast, you're not going to change it that much. So what does that mean? The wavelength of a person. I mean, obviously, when we look at Hannah, she doesn't look like this, right? She doesn't look like a wave. She looks like a particle. But you actually are a particle. You actually do have a wave nature. All of us do. So this is kind of the, well, her radius from heart to shoulder is probably about a half a meter. So her size is 0.5 meters. So what I want you guys to do is compare her wavelength to her size. And this goes for all of us. So look at Josh, look at her wavelength compared to her size. That wavelength is incredibly small, right? Incredibly tiny. It is so tiny that it's insignificant. Okay, so your wave nature is 0.0000000000000001%. Your wave nature is so small that it doesn't matter that you've got a wavelength and a frequency. Okay, but let's calculate it for an electron. So this is for a person. For an electron. Now the mass of the electron is found on appendix I. I've been saying J, but I meant I. So appendix I, Amanda, is where you find all these masses. And the mass of the electron, M subscript E, is 9.1 times 10 to the negative 31st kilograms. I have that memorized because I'm a dork, okay? But for the rest of you, you need to look it up on appendix I. How fast does an electron travel? Pretty fast, not quite the speed of light, but close to the speed of light. So I'm just gonna throw a number out there, 2 times 10 to the 8th. So when I calculate the wavelength of the electron, that's 6.626 times 10 to the negative 34th joules seconds per 1 electron. Divided by that speed, divided by 9.1 times 10 to the negative 31st kilograms. So now I'm going to plug that in, find my wavelength with the electron. There's the wavelength of the electron. So now let's compare this to the size of an electron. The radius of an electron is approximately 1 × 10⁻12 meters. Sorry, 13. I said 12, I meant 13. The radius of the electron is approximately 1 × 10⁻13. So now compare those two, Amanda. Who's bigger, the radius of the electron or the wavelength of the electron? The wavelength is now bigger than the object itself. For people, our wavelength is incredibly small compared to our size. So our wavelength and our frequency don't matter. But for the electron, its wavelength is actually bigger than the object itself. So then what does that mean? It means that you can't actually locate the object. So when your wavelength is tiny, well, think about it. A sound wave. Where's my sound wave? Can you point to where my sound wave is? No, because it's a wave. It's everywhere. So if an electron has a very big wave-like property, you are not able to point to, there's the electron, that's where it is. It's everywhere. And that's why we didn't teach you guys this stuff in middle school, because it's very hard for you to sit there and say, what? You're telling me the electron is everywhere. Yes, just like a sound wave is everywhere, okay? Now we can kind of make good guesses as to where the electron is, but we can't know for certain. And kind of the best analogy I can give you is a tuning fork. So I'm gonna maybe have Atticus here film me. I hold up this tuning fork, you can all see it, right? Looks nice and clear. The position is what we would say is definite. The wavelength is 0. But what happens if I give it a wavelength bigger than its size? And its size is about 2.5 centimeters. I'm going to give it a wavelength of 3 centimeters. And then let's see what happens to it. You always use a soft rubber, because if you hit it against something hard, it might break. So now it appears blurry, right? Now, I don't know if it'll pick it up on TV, how it's now blurry because of, and I'm just gonna walk around the room for a second and show it to everybody else. You guys can stare at that. You see how it seems kind of blurry to you? Blurry. Right? Doesn't look nice and clear. Blurry. So if you were to look at the electron, it would look blurry to you. Okay, more blurry than that tuning fork. Slow, blurry that you wouldn't be able to say, there it is. Okay, you could make guesses as to where it is. Okay, and that takes us to the Heisenberg Uncertainty principle. You don't want a picture of me, sorry. Sorry to scare everybody. All right. All right, so the Heisenberg uncertainty principle can be stated a number of ways. So first we'll just talk about it theoretically, okay? So for objects that are moving slow and have lots of mass, they're gonna have a small wavelength compared to their size, so it's not gonna matter, okay? Like people and baseballs and cannonballs. So imagine if I throw a baseball. And someone is over here and they want to measure the speed of the baseball using a radar gun. This is what the police do when they try to measure your speed. So the radar wave travels out, it hits the baseball, and then the wave comes back, and you can measure the time it takes for the radar wave to go there and back. Okay, that's how they measure your speed. Okay, does the radar light affect the baseball at all? No. Okay, but what happens if you're an electron? So I throw my electron, going this way, and then I stand over here, and now I use my radar gun against the electron. The electron is very, very small. It has very, very little mass. So when the light wave hits it, we already learned from Bohr, how do you excite an electron? Hit it with light, right? So when that light energy hits the electron absorbs that energy, and the electron will be deflected from its path. So by trying to measure the position of the electron, you actually changed its position. By trying to measure the speed of the electron, you actually changed its speed. Imagine if you're driving down Verona Road at 50 miles an hour, and the police officer turns on the radar gun and makes you speed up to 80. That's what happens with the electron. So you can't know the speed of the electron. Neither can you know its position. So therefore, the Heisenberg uncertainty principle, and there are a lot of ways you can write this, you can never be certain of the position of the electron. You can only know its most likely location. We will write the equation on the next page. So this is, in words, you can never know the location of the electron. The best thing you can do is find its probable location. The other thing that I'm just going to point out here is this is basically classical mechanics. Here's the scientist. When the scientist measures the speed of the baseball, does the scientist affect the baseball? No, right? Nothing happens. But down here, does the scientist affect the electron? Yes. So now the scientist has become part of the experiment. The scientist is now affecting the outcome, which, that shouldn't be, right? We should get the same answer no matter who runs the experiment. But now we're saying the outcome is dependent upon the scientist, okay? All right, so in equation form, the equation is delta x times m times delta v is greater than or equal to h over 4 pi. So delta x times m times delta v is greater than or equal to h over 4 pi. Delta x is the uncertainty in your position. Mass is mass in kilograms. We're always in kilograms. And delta v is the uncertainty in speed. Or I should say velocity. The physics teachers would get angry at me if I said v stood for speed. V is velocity. Any questions at home so far, you Zoomies? All right, so let's do our example here, and something got cut off. Calculate the uncertainty in position of a 1,000 kilogram car moving at 3 miles per second. So no, 3 meters per second, right? 3 meters per second plus or minus 0.2 meters per second. That's the part that got cut off. So calculate the uncertainty in position of a 1,000 kilogram car at 3 meters per second plus or minus 0.2 meters per second. You feeling okay, Elise? Or no?
Yeah.
Okay, just checking. All right. So we know our mass, 1,000 kilograms. Do not confuse the speed and the uncertainty in the speed. Okay. So if I am driving 60 miles an hour, and I brake to 50 miles an hour. So I was driving 60, I brake, and now I'm going 50. What's my change in velocity? 10, right? What's my velocity? 50, right? I'm still driving 50, but my change is 10. So don't confuse the change with the speed. So this is my speed. I'm going 3 miles per second. In fact, maybe I'll just write that down there, 3 meters per second. But my change is this guy, the plus or minus, okay? So my delta V is the 0.2. We don't actually need this. Nowhere in the equation do we have V. We have delta V. So I just want to point that out, you know, as you go on in science and in this class, the difference between V and delta V. Now we can plug our stuff in. We're going to solve for uncertainty in position. That's what we're looking for. I don't care about that. So let's just start off with our equation. Do the algebra. So now I'm left with delta x is greater than or equal to h over 4 pi m delta v. So always do the algebra first, then Hillary, then you can start plugging the numbers in. So my delta x is going to be greater than or equal to, how many cars do we have here, Allison? One or a mole of them? Allison says just one car. The problem says a car. So if it's a car, it's one car. Divide by 4, divide by pi, divide by my mass in kilograms, divide by my change in velocity, and now I can calculate my delta x. And I get 2.6 times 10 to the negative 37th meters. So what does that mean, the uncertainty in position? So how big is a car? Car is about 3 meters long, right? Well, the uncertainty is plus or minus 2.6 times 10 to the negative 37. So when you look at a car, does it appear blurry to you? Nope. Not like that tuning fork, right? You looked at the tuning fork looked blurry. The uncertainty in position of the car is way too small to map, okay? It's insignificant. Now we could redo this calculation and do it for an electron. The electron has a much, much smaller mass. Then the uncertainty in position is going to become big. We could also change the velocity. That would also affect it. So let's say we sped the car up to the speed of light, made the car go super duper duper fast. This is what it would look like. Sped the car up to the speed of light. You don't need to draw this picture. I'm just going to show you the picture. So we sped a car up to the speed of light. That's what it would look like. Now, can you tell me where the car is? The uncertainty has become too large. Now all you see is a blur. Now you can make some good guesses as to where the car is. Is the car over there? No. Is the car over here? Probably. Is the car right there? No. So that's what happens with quantum mechanics, is we only can start guessing. Okay, we're not able to say with certainty what's going on. Okay. So those are the last two problems we had to learn for the test. So you should be able to do the worksheet now and the practice test, okay? There's one last thing I'm gonna do, and that is, we got one more page here to summarize. I'm gonna add that in. So if we're going to summarize the difference between classical mechanics and quantum mechanics, classical mechanics works for large objects. And when I mean large, I mean bigger than an atom. So basically anything bigger than an atom follows classical mechanics. Quantum mechanics is atoms or smaller. The other thing is quantum mechanics is for very fast moving objects. And when I mean fast, I mean near speed of light. 1,000,000 miles an hour isn't fast enough. That's still too slow. And classical mechanics is slow. And then the other big difference between quantum mechanics and classical mechanics is quantum mechanics is probabilistic. Meaning the best thing we can do is give a good guess. There are many possible answers. Or outcomes is another way to say it, many possible outcomes. Whereas in classical mechanics, there's only one, we call it deterministic. There's only one answer, one possible outcome. So when you take classical mechanics next year in physics, you'll do things like, how long does it take for a penny to drop off of the Empire State Building? 12.2 seconds. That's the answer. In quantum mechanics, you'd say, well, it depends. So that's the difference between classical and quantum mechanics, okay? So everything up until letter K is like the math stuff. So starting probably next week, Thursday, the last 5 pages of notes is all the theory stuff, okay? But I do want to just go back and talk about Heisenberg for a second. And then you'll have work time. I'm just going to switch over to the computer. Nah, I'm not going to switch over to the computer. I'm going to stop my screen share for just a moment, okay? So just sit tight, guys, at home. Don't worry, I'm not going to abandon you. Just sit tight. I'm just trying to upload something. We'll see if this works. too pixelated. Okay, I'm going to do this. All right, I'm going to show you a picture. I want you to tell me what you see. So what do you see in that picture, EJ?
Oh, isn't this the one where you can see two? This is some like old woman. She was one where the young lady.
So what is this a picture of? So Jordan says this is a picture of a young lady. What do you think, Sanuja? What is it a picture of?
An old lady.
Oh,
I've
there's
seen
an
this
argument.
before. It's both of them, isn't it?
There's a fight going on. Sanuja says old lady, and Jordan says young lady.
Oh, the young lady's chin is the old lady's nose, and the young lady's ear is the old lady's eye.
So who's right? Who sees a young lady? Raise your hand. Give me a thumbs up at home if you see a young lady.
I see both.
Raise your hand if you see an old lady, or give me a thumbs up if you see an old lady. Okay, so I don't know if it makes it worse in notability or not, but the old lady, there's one eye, there's another eye, there's her nose, and there's her mouth. Okay, whoops. So that's the old lady. The young lady is looking away from you. That's her eyelash. That's her ear. That's her jawbone. And that's a choker necklace. She's looking away from you. So this is a picture of, what is it a picture of? It's a picture of, that's a good question. Who decides what's it a picture of? You do. You decide if you see it as an old lady or a young lady. You control it. So Atticus can look at it and say young lady, and Haley can look at it and say old lady. Is one of them wrong? So you have to start thinking of the electron as this picture. So I could hold an electron in my hand. Haley would look at it and say it is obviously a wave. And Atticus would look at it and say it's obviously a particle, just like this picture. And what is the true nature? It's both at the same time. Okay, the picture doesn't change. The picture doesn't become a young woman and then all of a sudden go boom, 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 old lady. And then go boom, 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 and switch back to young lady. The picture's not changing. So don't think of an electron as a baseball and then all of a sudden it becomes a wave and then it turns back into a baseball. It's both at the same time. Okay, the electron is both at the same time. You decide what you want to see. And this is why quantum mechanics becomes really kind of funky dunky, is that everybody will perceive it differently, which means there is no ultimate perception. There's no ultimate reality. In other words, Jordan, there is many universes as there are people, because every single person is going to perceive the universe differently. So we can't just say there's one universe, okay? Because we're all going to look at it differently. So that's why quantum mechanics, like I said at the very beginning, how 800 years ago, most people thought of the world as flat and only a few people saw it as round. Most people don't know quantum mechanics. They're still thinking of the world, the universe, as this machine that's fixed. But it's not that way. It's like the universe is like this picture. All right, so I promised I would stop at 9:20, right? Actually, any parting comments or questions or? Well, I'm actually quite hopeful that you will actually get all your homework done in class. So your homework is to do quantum worksheet number 1. Oh, now. So there's quantum worksheet number 1. The math test is due on Wednesday, and that's the day we'll take the test. So we'll review first, and then we'll take the test, okay? So we'll review the first half hour of class, and then you'll take the test in the last hour of class, okay? So there's nothing prohibiting you from working ahead here, Henry. You could do the quantum worksheet and then do the practice test if you like. Or you could wait to do the practice test Tuesday night. That's totally up to you, okay? So you've got plenty of time. We got class time, Friday night, Saturday, Sunday, Monday. So, all right, so now I promise to shut up. If you guys want to work in small groups, as long as you're 3 feet away, I'm fine with that. I will come by and help you. Addie, Amanda, Charlie, Josh, Sanuja, Simon, Wyatt, do you have any questions about what you're supposed to be doing right now? I think I'm gonna mute myself because people say when I'm talking, it gets annoying. So I will have the chat room up. So I will check the chat to see, and I will check in with you guys every 5-10 minutes to see if you have any questions, okay?
Question on it. Are we gonna have like this stuff on it?
So I've been putting a few helpful hints in the chat room for you guys at home. Does anybody have any questions? I've been checking the chat and no one's put anything in there. Sanuja, you have any questions?
No, I'm good.
Simon, you okay? Charles, you all right? Okay, Addie, Josh, and Sanuja, and Simon, I want you guys to pay attention for a second. I'm gonna do number 6. I forgot about number 6, so we're all gonna do number 6 together. Sorry.
Mr. Strauss, what does it say on the table? When we did the electron column together in class, you said 2 times 1 times 10 to the negative.
These things always have to be in kilograms. Okay, so I'm just gonna do number 6 here. So I'm gonna read the problem. So number 6 says, I've got an electron and my velocity is somewhere between 2.3 times 10 to the 8th and 2.5 times 10 to the 8th. Okay, so if my velocity is somewhere between these two numbers, so my velocity is between those. It's kind of like saying, I'm going somewhere between 40 and 60 miles an hour. My uncertainty would be 20, right? So if I'm going between those two numbers, my uncertainty is 0.2, okay? So the uncertainty in that problem is 0.2. The answer for that problem is wrong for number 6. I did not put it into my calculator correctly. So we know the mass of the electron is 9.1 times 10 to the negative 31st kilograms. So my equation would be delta x is m delta v greater than or equal to h over 4 pi. Now you should be able to finish the problem off because you have your delta V, you've got your mass. I'm gonna quick calculate the correct answer for you. Okay. The correct answer is 2.8 times 10 to the negative 12. So 2.9. Okay. That's the correct answer for number 6. Okay. Sorry about that. That's the correct answer for number 6. Okay. And again, with all the homework problems, I grade on completion. I just, just try them. Okay. So hopefully Addie, Josh, Sanuja, and Simon, you saw that. No, I'm screen sharing. 1 second. 5A? No, it's not a trick question.
Oh, you did one. Oh, okay. This answer is the same. Answer the question. I lied.
Yes. I want to highlight your number. Oh, so that's why I put that in there. When you look at the workbook, they don't. Which I wish they would, because then students use a lot of constantly.
No.
Well, no, that's not for one of them. So this is not the real thing. So momentum. So the mass direction. So there is an equation. You guys, that's the one. So then it's the speed. And then the other thing is obviously quick units. And that's 142 pounds. Must convert to kilograms. You guys have a great day, okay? And Addie, Josh, if you have questions over the weekend, don't hesitate to email me, okay?